In section 3.3, our objective is to use derivatives to determine where a function is increasing and decreasing and use this information to find relative extrema. Let's begin with increasing and decreasing functions. A function is increasing if for any two numbers, x sub 1 and x sub 2 in the interval, x sub 1 being less than x sub 2 implies f of x sub 1 will be less than f of x sub 2. Simply put, as x grows, or as we move left to right in the function, so as we go right, as x grows, y grows. Y gets bigger. Or thinking of it directionally, it goes up. The graph goes up. Y goes up. A function is decreasing if for any two numbers x sub 1 and x sub 2 in the interval, x sub 1 less than x sub 2 implies f of x sub 1 will be greater than f of x sub 2. Simply put, as x grows, because we always read a graph going left to right, just like we read words, y gets smaller. Or we think of the graph going down. Simply just think of the graph going down as we read left to right. So increasing, we're thinking of where y goes up. Decreasing, we're thinking of where the y goes down, simply put. And then we can say, well, a visual, so going up and going down. And then we can say that a function is strictly monotonic on an interval if it's either increasing on the entire interval or decreasing on the entire interval. You know how monotonic, nothing ever changes, so always increasing. It can be a change of an increase, but that's the type of function when we say monotonic. Strictly increasing on the entire interval would look something like that. Examples to identify the open intervals where the function is increasing, decreasing, and constant, and stating which functions are strictly monotonic. So I see a function increasing, decreasing, increasing, decreasing. It is not strictly monotonic. Let's say where I see increasing. So up to this x value, and I always give locations as x values. So this is at -3 that it stops increasing. So our function is increasing on the interval -∞ up to -3. And then from -1 up to 2, and then it doesn't increase anywhere else. The function is decreasing, looks like everywhere else, going down, literally going down. Each y value is smaller than the y value before it. So from -3 to -1, and from 2 to infinity because of that arrow. In this one, the function is always going up. It's going up at different rates, but it's always going up. So this function is increasing -∞ to infinity. Therefore, because it's always increasing, this function is strictly monotonic. This function, I see this branch increasing. If I draw the next branch, also increasing. Therefore, increasing on every interval I can write, -∞ up to, this looks like -2, union with -2 up to infinity. However, because this y value is smaller than a y value that came right before it, like this one, we can't really describe this as strictly monotonic. We're going to talk about why in a later section that we don't really want to call this strictly monotonic. In this one, I see increasing just in this section right here. So from -1 up to 1 and not increasing anywhere else. Let's look at where it is decreasing. Here I have a hole, so I have to pause at that spot at -3. So -∞, because of the arrow, up to -3, but it's not doing anything at that point, so I can't include it in the interval, but then I'm decreasing again up until -1. So pick up again at -3 up to -1, and then the rest of the way it's constant after 1. So constant from 1 to infinity. Now remember,